Imagine holding a compass in your palm. The needle quivers, settles, and points north in ancient gesture, a quiet whisper from the planet itself. That small motion is a clue to something immense, an invisible field, wrapping Earth in a protective embrace. It doesn't glint under sunlight, and you can't touch it like soil or rock. But it is there, humming softly across continents, flowing over oceans, seeping through forests, reaching up into the breath-thin sky. It is the planet's magnetic field, and without it, our world would be a very different place, harsh, stripped, and much less welcoming to the fragile chemistry we call life. Take a slow breath. Imagine the space around our planet as a delicate glass sphere. Now imagine that sphere buffeted every second by a fast, invisible wind made of charged particles streaming from the sun. This is the solar wind, a river of plasma electrons and protons, racing outward, carrying with it the sun's magnetic temperament. In that gentle storm of space, Earth carries its own quiet strength, a magnetic field that bends and shapes the incoming wind, forming a protective cocoon called the magnetosphere. To the solar wind, our planet isn't just a rock. It's a magnetic presence that says, "Not here, not so fast, not all the way in." When the solar wind presses in, the magnetic field yields like fabric and then pushes back. It gathers the streaming particles, redirects them, and shepherds them along its lines. Some slip down toward the poles, where the field lines dive into the atmosphere and release a gift. Auroras, curtains of light, green and violet, blue and red, dancing like breath over winter nights. Those lights are not only beautiful, they're a visible sign that our invisible shield is working. The sky glows, and life below remains quiet and largely undisturbed. It's simple to say, Earth has a magnetic field, but the simple fact hides a profound promise. Our atmosphere is not simply left alone, it is defended. Energetic particles that could crack the delicate molecules of DNA are steered away. The relentless heat and force of the solar wind, which can strip gases from a world over millions of years, is tamed and softened by our planet's magnetic reach. Without it, our atmosphere could thin like breath on a cold window, our skies losing the ancient ingredients that living things require. With it, water remains, oxygen lingers, and the story of life has time to unfold. Picture the field lines as strands of silk rising from the southern hemisphere, arcing high overhead and diving back down in the north. If you could see them, the sky would be filled with invisible geometry. Loops, arches, and smooth curves, all moving slowly as the planet turns. These lines guide charged particles like rails guide a train. They trap some, creating donut-shaped reservoirs of high-energy particles called the Van Allen belts. They deflect others, reflect still more, and in doing so, they govern the space weather around us. A delicate, breathing shelter. This is one way to understand Earth's magnetic field, a guardian at the boundary of space. But there's another layer, closer and more personal. Even at ground level, there's a kind of quiet presence. Birds feel it when they migrate. Turtles sense it when they return to ancient shores. Honeybees, salmon, even certain bacteria carry tiny compasses within them, tuned to the same field that steadies a needle in your hand. The field doesn't shout. It whispers, and life has learned to listen. The field is not perfect, and it does not need to be. It shifts, it drifts, it breathes. The North Magnetic Pole wanders like a slow pilgrim across the Arctic. Its strength rises and falls over centuries. In some places over the South Atlantic, the shield is thinner than elsewhere. A softened patch in the armor we call the South Atlantic anomaly. Yet even as it ebbs and flows, even as it changes shape under the pressure of the sun, it holds the line. Day after day, year after year. A ceaseless, quiet work. At night, when the world grows still, that work continues. Satellites trace their arcs within its shelter. The International Space Station rides inside the Magnetosphere, dipping occasionally into regions of higher radiation, but spared the full brunt of cosmic particles that churn in interstellar space. Airline pilots, flying over polar routes, feel the magnetic latitudes in their equipment, and sometimes in their procedures, adjusting when solar storms flare. Power grids hum with a slight awareness of the field's moods, because intense solar storms can set the planet's magnetic veil vibrating, stirring electric currents in the ground. Everything from birds to circuit boards, from auroras to compasses, is wrapped in this quiet relationship. You don't need to know equations to feel the significance. Imagine sitting under a winter sky as auroral light drapes the horizon. There's a soft crackling of snow, the cold air resting on your cheeks, your breath a slow cloud. Above you, the earth meets the sun's wind and turns that pressure into a dance. That is our shield, turning danger into beauty. A thin, ghostly stage for light, saving the heavy blows for itself. But how does a planet made of rock and iron weave such an astonishing garment? What quiet engine turns deep in the dark to keep this field alive? To understand how Earth's magnetic field keeps us alive, we have to journey inward to the molten heart of the planet, and outward to the edge of space, and along the winding path of history, where sailors, physicists, and dreamers piece together the story of an invisible force. Let's walk slowly, step by step, into the planet's magnetic breath, and discover how it came to cradle the fragile, luminous story of life. Close your eyes for a moment and picture a ship at sea, the horizon gently heaving under a pale sky. In the age before satellites, before radio, before the hush and hiss of weather maps, sailors stood at the rail and learned to read the world. They watched the stars, the swell, the flight of birds. And in their hands, a small disk with a needle, a compass, quietly pointed away. That small, ordinary instrument, so simple, opened the idea that Earth itself was magnetic. The knowledge is older than any one voyage. In ancient China, long before compasses guided sailors across oceans, there were lodestones, naturally magnetized pieces of iron ore that could pull on metal and align with Earth's field. Stories tell of spoon-shaped lodestones pivoting toward the south, of fortune-tellers and philosophers observing a mineral that seemed to have a preference, a sense of direction. To later minds, the wonder deepened. Why should a stone know north? Centuries passed. In the late 1500s, an English physician named William Gilbert held a small sphere of magnetized iron, a tyrella, and watched a compass needle slide across its surface. He had an idea both bold and elegant. Perhaps the Earth itself is a giant magnet. The compass doesn't chase some distant star or respond to a hidden wind. It aligns to a field that rises from the planet's interior. Gilbert's book, The Magnet, gathered the fragments of magnet lore into a first scientific embrace, a calm voice saying, "Here is a force. Here is a pattern. Here is Earth behaving like a magnet in the hand of nature. Walk on a beach today and look down. The sand may hold tiny grains of magnetite, iron oxide polished by waves and time. Touch a simple magnet to the sand, and they rise into little black whiskers, aligning along unseen lines. That is a small echo of the field that cradles us." Nearby, a bird lifts from the shore and turns toward a distant line of trees. Somewhere within its cells, perhaps in the protein cryptochrome in its eye, a light-triggered chemical reaction whispers to the bird about direction, a quantum-scale compass tuned to the faint tug of Earth's magnetism. The bird doesn't know the equations. It feels a map the way you feel the warmth of the sun, directly, quietly, and with a memory deep as the species itself. What is a magnetic field in human terms? Think of it as a way that space itself is instructed to nudge charged particles, electrons, and protons along a path. It is not a substance, not a sheet you can fold. It's a pattern, a geometry of influence. Where there is a magnetic field, an electron curves, a proton spirals, a compass needle aligns. Invisible lines of force loop from near Antarctica to near the Arctic, and back again, and every patch of sky, every raindrop, every tree and rooftop lives inside that pattern. Though the word north suggests a steady destination, Earth's magnetic north is a wanderer. It slides across the ice, miles each year, drifting toward Siberia. It moves as the field that shapes it shifts, a restless dance driven by motions in the planet's interior. The field also tilts slightly from the planet's spin axis, and it changes strength over time, growing stronger in some regions, weaker in others, like the slow pulse of a sleeping animal. These variations have their own quiet language, one that scientists have learned to hear with sensitive instruments spread across continents and carried into orbit. There is a sensory richness to the field that we've learned to appreciate with patient, careful listening. In 1835, a mathematician Carl Friedrich Gauss developed a method to measure the absolute strength of Earth's magnetic field. He built a magnetic observatory and turned the field into numbers into a map. Later, Edward Sabine linked magnetic storms recorded on Earth to sunspots observed on the solar surface, tying our planet's magnetic life to the moods of our star. The sun and Earth, we learned, are not separate worlds. They are partners in a quiet, electric dance. Imagine a long wire buried in soil, a loop running around a meadow. On a calm day, very little stirs in that wire. During a solar storm, when the sun throws a cloud of charged particles across space, and the magnetosphere flexes and sways, faint currents can seep into that loop, a slow-motion breath exhaled by the planet itself. The field moves, and with it, electric currents ripple through the ground, through metal, through power lines. Today, engineers gently monitor this breathing, because in rare, powerful storms, the currents can swell and strain the quiet machinery of our modern life. Move from the ground to the edge of space, and the field shows another face. There, above the clouds, lies the ionosphere, a tenuous shell, where solar radiation strips electrons from atoms and molecules, leaving ions behind. The ionosphere is like a shimmering skin, responsive to the sun, to auroras, to lightning. Earth's magnetic field threads through it. Radio waves skim along it, bounce from it, bend with it. Long before fiber optic cables stitched continents together, radio operators listened to the ionosphere and heard the planet's changing space weather in the static and the hiss. Today, we still rely on that complex, living interface for GPS signals, communications, and a sense of the planet's calm or unrest. If you could ride a particle, a tiny charged bead released by a solar flare, you'd feel the field as a guiding hand. Near Earth, you'd spiral around the magnetic lines, bouncing between the north and south where the lines converge. Some of your companions would be captured, becoming part of the Van Allen belts, two smooth toruses wrapped around the planet. Others would be steered harmlessly away into the long flowing tail of the magnetosphere, dragged out by the solar wind to many Earth radii behind our world. You'd feel gentleness in the deflection and stern firmness in the boundaries. The rules are clear, quiet, and precise. The field shapes your path. And beneath all of this, beneath the auroras, beneath the migrating birds, beneath the drifting pole, there is a question that pulls us inward. If Earth is a magnet, then where is its magnet? A bar magnet hidden under the crust? Something solid, crystalline, and permanent? The truth is stranger and more beautiful. There is no fixed magnet at the center of the Earth, the way there is a magnet glued under a piece of paper to pattern iron filings. There is, instead, a restless, swirling ocean of liquid metal, turned by heat and rotation into a self-sustaining electrical storm. It is motion, not stillness, that gives rise to the quiet canopy above us. In a few moments, we'll descend in our imaginations through rock and fracture, through mantle, and into the core. We'll listen for the slow churn of molten iron, the whisper of rising plumes, the subtle twist of the planet's spin. From those motions, a field is born, made, and remade every second for billions of years. The compass in your hand, the aurora in the sky, the safe air you breathe, they are all threads in this deeper tapestry. How does the Earth's heart keep beating? And how does that beat build a shield around a world? Let's go inward, calmly, and find the furnace where magnetism is forged. Imagine standing on solid ground, feeling the reassuring weight of stone beneath your feet. Now let your mind drop through it, slowly, as if the Earth were a book you could open. You pass through the crust thin, like a skin. You move into the mantle thick, hot, solid, but flowing over deep time. And then, deeper, you reach the core. First, the outer core, a sphere of molten iron alloy, hotter than the surface of the sun, but under pressure so immense that the iron chooses to flow rather than burn. Deeper still lies the inner core, a solid ball, crystallized iron-nickel, slowly growing as the planet cools. Here, in the outer core's liquid metal, is where the magnetic miracle happens. The geodynamo, a soft word for a profound process, arises from motion. The outer core is not quiet. It churns. Heat escapes from the planet's youth and from the slow crystallization of the inner core, where iron freezes and rejects lighter elements. That compositional difference drives buoyant plumes. Hot, iron-rich fluid rises. Cooler fluid sinks. The Earth rotates, and the Coriolis effect twists the rising columns into spirals, organizing the flow into graceful helical structures. Where conductive fluid moves through its own weak magnetic field, it generates electric currents. Those currents create magnetic fields, which in turn guide the fluid motion, which strengthens the currents, and the loop closes. A self-exciting dynamo. Motion giving rise to magnetism, magnetism guiding motion. A quiet, cosmic engine. It's a romance of physics that began in the imaginations of scientists more than a century ago. In 1919, the physicist Joseph Larmor proposed that magnetic fields in cosmic bodies could be generated by motions of conductive fluids, a dynamo idea. Later, in the 20th century, Walter Althusser, Edward Bullard, and others built the theoretical scaffolding, translating the poetry into equations. They explored how turbulence and rotation could sustain a field for billions of years. The math is intense, but the picture can be felt. The Earth's heart is a swirling, electrically conductive ocean, and that motion makes a magnetic lantern that the planet carries into space. This is not a lantern that burns with a steady, unwavering glow. The field waxes and wanes. It tilts. It wobbles. Every few 100,000 years, on average, it does something remarkable. It flips. North becomes south. South becomes north. These geomagnetic reversals are recorded in basalt like memories. When lava erupts on the seafloor and cools, iron-bearing minerals within align with the field like tiny compass needles. They freeze in place, a snapshot of the magnetic moment. As the seafloor spreads, parallel stripes of reversed and normal magnetization form, mirrored on either side of mid-ocean ridges. In the 1960s, scientists Frederick Vine, Truman Matthews, and Lawrence Morley read those stripes and discovered a story of moving continents and a flipping field. Paleomagnetism, the study of these magnetic fossils, turned the ocean floor into a time machine. Reversals are not failures. They are normal breaths in the dynamo's long life. During a reversal, the field weakens, becomes more complex, and then recovers with poles swapped. Life persists. The magnetosphere persists, though thinner in places, more permeable to solar storms. The record shows no mass extinctions tied to these flips. The shield is resilient, even as its architecture briefly re-evaluates itself. That resilience is part of the quiet reassurance this field offers. It is a living system, alive in the sense that it changes and adapts, clumsy for a while, then graceful again. In the 19th century, Christian Birkeland, a Norwegian scientist, tried to recreate auroras on Earth. He built a little magnetized sphere, a terrella, and placed it in a glass chamber, and fired beams of electrons at it. Glowing rings formed near the poles. He dreamed of currents in space that flowed along Earth's magnetic field lines, connecting the solar wind with our atmosphere. Decades later, satellites confirmed his intuition. There are indeed currents, Birkeland currents, that carry energy from the solar wind into the auroral zones, feeding the lights we see with the sun's distant weather. The field is not just a shield. It is a conductor of sorts, a pathway for energy to become light. In 1958, the Explorer-1 satellite detected radiation belts around Earth, later named for James Van Allen. These belts, shaped by the field, store energetic particles. They are both a challenge and a blessing. A challenge to spacecraft that must pass through them. A blessing because they can find and manage particles that might otherwise do more harm at lower altitudes. The belts are like moats around a castle, not comfortable to occupy, but part of a defense that keeps the inner spaces calmer. There are storms in this magnetic world. In 1859, the Sun launched an enormous flare and a coronal mass ejection aimed at Earth. The result, when it arrived, was the most powerful geomagnetic storm on record, the Carrington event. Telegraph systems sparked. Operators received shocks. Auroras glowed in Korean skies. Today, a storm like that would test our infrastructure satellites, power grids, and communications. But the magnetosphere still would stand between us and the raw fury of the solar wind, turning brute force into shimmering skies and manageable currents. The shield does not eliminate risk. It transforms it into something we can endure and understand. Modern missions watch the magnetosphere with tender attention. ESI's swarm satellites trace the field's variations with exquisite sensitivity, teasing apart the contributions from the core, the crust, the oceans, and the ionosphere. NASA's Themis and MMS missions untangle the physics of magnetic reconnection, where field lines break and rejoin, releasing energy like sudden sighs. We have discovered that the magnetosphere is not a simple static bubble. It is a dynamic, responsive, permeable architecture. It can open a little on the day side, letting energy in, and grow a long tail on the night side, where reconnection can fling particles back toward the poles to paint auroral arcs. Meanwhile, in laboratories, researchers spin vats of liquid sodium, seeking to mimic the Geodynamo. In the heart of these experiments, vortices twist and currents spark. The experiments are clumsy compared to the planet's refined dance, but they give us a tactile sense. Yes, motion in a conductor can make a field. Yes, rotation organizes that motion. Yes, a field can grow from almost nothing and sustain itself. We understand enough to feel awe. We recognize enough to accept mystery. There are still subtleties, the precise balance of heat flow across the core mantle boundary, the role of light elements like sulfur, oxygen, or silicon in the core, the timing of the inner core's birth that we listen for like a faint heartbeat under a stethoscope. All of this observations, theories, histories leads us to a gentle realization. Earth's magnetic field is not an add-on, not a decorative ribbon tied around a finished world. It is part of the planet's very metabolism. It stands at the edge, shaping the space weather that meets our atmosphere. And it rises from the center, born of deep heat and slow crystallization. It reaches outward and inward, stitching core to sky, physics to biology, past to future. Now, turn your gaze from Earth to its neighbors. Mars whispers from the dark with a thin sky, a faint trace of what might have once been. Mercury spins, small and close to the Sun, with a weak field that raises questions I'll invite you to ponder. The presence or absence of a magnetic shield changes the story a planet can tell. So let's drift outward, carried by calm curiosity, and see what happens to worlds without such a quiet protector. Picture Mars under a clear, salmon-colored sky. The wind moves dust softly, but the air is thin, less than 1% of Earth's sea level pressure. Once we think Mars had rivers and lakes, perhaps even a northern ocean. Its surface is carved with valleys that look like the work of water. Where did that water go? Where did the thick atmosphere go? Part of the answer lies in magnetism, in the difference between a world that holds an active magnetic shield and one that does not. Mars today lacks a global magnetic field. Its crust holds local patches of remnant magnetization, magnetic memories, frozen from a time early in its history, when a dynamo may have turned in its core, but the global shield is gone. When the sun's wind arrives at Mars, it meets little resistance. The wind can reach down and stir the upper atmosphere, lifting atoms and peeling them away. The MAVEN mission has measured this loss, watching ions stream down the solar wind's path. Over billions of years, the solar wind acts like a persistent, patient sculptor, removing gases, thinning the sky. Add to that the planet's smaller size, easier for molecules to escape from, and you can begin to see why Mars today is a dry, cold habitat battered by radiation. With less shielding, more energetic particles strike the air, generating chemical reactions that can erode ozone and alter climate chemistry. On the ground, radiation doses are higher. Life, if it exists there now, would need to be tough, hidden, shielded in rock or ice. Now turn to Mercury, a world so close to the sun that the solar wind howls past like a constant gale. Mercury, surprisingly, does have a magnetic field, though it is weak, about 1% as strong as Earth's at the surface. NASA's Messenger spacecraft revealed a field that is off-center and subtle, and an environment shaped by intense space weather. Mercury shows us that a small planet can sustain a dynamo, but that proximity to the sun and planetary size complicate the story. The lesson is clear. Every planet's magnetic life is particular. There is no single blueprint. There is a balance of heat, rotation, composition, and time. Now return gently to Earth, held between the two, larger than Mars, farther than Mercury, brimming with liquid water and a thick, kind atmosphere. Our magnetic field helps in two ways. It deflects and channels charged particles that could break molecules and heat the upper atmosphere. And it slows the escape of light gases by preventing the solar wind from reaching deep and energizing the air. It is not a perfect lid. A magnetosphere is porous and complex, but it is a gardener's wall, keeping out the larger, hungrier animals so that the tender plants can grow. Behind the wall, weather can be water-driven, not plasma-driven. Chemistry can be shaped by sunlight and biology, not dominated by space storms. We can sense the field's protective nature in modern discomforts. Consider satellites. In certain regions, like the South Atlantic anomaly, a dip in the field's strength, caused by the offset, tilted nature of our geomagnetism radiation levels are higher. Satellites passing through must be resilient. Instruments may glitch. The International Space Station alters operations when solar storms increase radiation, especially near the poles where protective field lines open downward. Airline flights along polar routes sometimes adjust altitudes or paths when geomagnetic storms rise to reduce radiation exposure and maintain communications. These are small, manageable accommodations, gentle reminders that the shield is there, doing most of the work, but asking us to pay attention. Think about us at ground level. Cosmic rays from distant supernova traverse space and reach our planet. Most are softened by the magnetosphere and absorbed by the atmosphere. By the time they reach sea level, their numbers and energies are greatly reduced. Our cells, evolved within this shielded environment, repair DNA with quiet efficiency. The magnetosphere's role is not to eliminate cosmic rays. Nothing can do that entirely, but to keep their rates and energies in a range that life, over time, has learned to endure. In this way, magnetism becomes a collaborator with biology, a partner in the long experiment of evolution. There is also the gentle mystery of animals, and magnetism a whispering thread between life and field. European robins seem to sense the magnetic field through light-sensitive molecules in their eyes. When blue light enters the eye, it triggers electrons to form a radical pair, a quantum duet whose spins and reactions are subtly influenced by Earth's magnetic field. The result, a kind of visual overlay, an awareness of direction woven into sight. Sea turtles hatch on dark beaches and crawl into the surf, imprinting on the shoreline's magnetic signature, later returning decades afterward to nest. Salmon leave rivers and cross the open ocean, guided among other cues by magnetic maps written in water. Even tiny bacteria, magnetotactic species, build chains of magnetic crystals inside their bodies, aligning like little compass needles to find chemical comfort in water and sediment. These are not just curiosities. They are examples of life tuning itself to the planet's quiet voice. If you listen to the sky through radio, you can hear the field's presence as well. The auroral oval, the ring around each pole, where auroras are likely sings in radio frequencies when charged particles rain down. The ionosphere crackles and sways, changing the travel of radio waves. Amateur radio operators learn to sense the sun's mood. They speak in soft jargon of SIDs and KP indices, but behind the acronyms is a felt experience. The magnetosphere has weather, and like wind shifting in a grove of trees, the field announces those shifts in 1,000 subtle ways. For exoplanets orbiting other stars, magnetism becomes part of our search for life. Around small, active stars, M-dwarfs flares are frequent and strong. Planets close enough to be warm might be battered by radiation. A magnetic field could help such planets keep their atmospheres, maintain surface water, and shelter biology. Astronomers are beginning to look for signs of exoplanet magnetism, radio emissions, auroral lines, star-planet interactions. It may be that when we one day find a truly Earth-like world, we'll ask, does it have a quiet shield? Does it carry a magnetic lantern into its sky? And then there is the question that touches the edge of our sleep. Will Earth's shield last? The Geodynamo needs heat and motion. As the inner core grows, it releases latent heat and light elements, buoying the outer core and sustaining convection. This has kept the dynamo alive for billions of years. But deep time is long and patient. There are episodes in the geological record around 565 million years ago when the field seems to have weakened dramatically, perhaps near the time the inner core began to nucleate. Afterward, the field strengthened. The story is not a straight line. It is a slow braid of cooling, crystallization, and stirring. One day, in a far future when the core cools enough, convection may falter and the dynamo may dim. But that day is not soon. And in any case, our sun will change too, brightening over eons, outpacing our magnet's decline. For now, and for ages yet, the field breathes. It wanders, it reverses, it sometimes thins in places and recovers. It partners with our atmosphere to protect oceans and forests, skin and seed, children and elders, turtles and robins. It paints auroras to remind us of the invisible work it does. And as we contemplate what it means to be alive on this world, this small blue lantern in a wide dark sea, the magnetic field becomes a kind of lullaby, an invisible hand smoothing the covers as we drift to sleep. Still, it is a lullaby with complexity, with questions we continue to ask. How exactly does the core's chemistry shape the field's patterns? Are there subtle links between field strength and climate, mediated through cosmic rays and clouds? What stories lie in ancient rocks we have not yet read, in ocean floor stripes still buried and waiting? In these questions, curiosity blossoms, and the next part of our journey leads to the future, to how we watch the field, how we live with it, and how we might carry its lessons beyond Earth. There's a comfort in standing at night under a sky threaded by Aurora, feeling the Earth turn beneath your shoes. It's the comfort of continuity. Our ancestors, who told stories of lights in the north, felt that comfort too, even without knowing plasma or dynamos. We know more now, and somehow the knowing makes the comfort deeper. To close our journey, let's linger with what the magnetic field means for our bodies, our technologies, our future, and our sense of belonging in the cosmos. Start with the body. Each of us carries a world of cells, quietly dividing, repairing, reading the script of DNA. Radiation is part of our environment. It writes occasional errors into the script. Our repair mechanisms catch many of them. Evolution adapts to the rest. The magnetosphere keeps the edits gentle. It turns a cosmic hailstorm into a manageable drizzle. It reduces the number of high-energy particles that would otherwise pierce the atmosphere and crack molecular bonds. At ground level, our dose is small. In mountains, slightly larger. In flight, larger still, but still softened by the field and the air. Even astronauts aboard the International Space Station, encased in aluminum and plastic, benefit from the field's reach. Their spacecraft loops within the magnetosphere, and although they see more radiation than we do, they are spared the hard, unfiltered rain that deep space travelers must confront. The magnetic field is not a wall, but it's a porch roof, enough to make the weather bearable, enough to let life thrive. Now the technologies that weave our world together, power grids, long lines of wire, can act like antennas for the slow electric surges induced by geomagnetic storms. Engineers design with this in mind, adding resistors and procedures. Satellites harden their electronics against radiation. Operators power down or change orientation during storms. Instruments are placed in orbits that balance exposure and utility. GPS signals skim the ionosphere. During disturbances, their paths wobble ever so slightly, and our maps adjust. We have learned to treat the magnetosphere as a changing weather system. We don't fear it. We respect it. Like sailors who read the swell to set their sails, we read magnetograms and solar images and adjust our technological rigging. There is a gentle romance in how the field connects us to other phenomena we cherish. The polar lights are one. Another is the soft crackle of meteors on radio, the flutter of long-distance signals at dawn and dusk, the quiet coordination that migratory creatures show in their seasonal arcs. Consider cows and deer aligning their bodies along north-south axes in calm conditions, an observation still debated, but suggestive. Consider homing pigeons losing their way when magnetic anomalies ripple the sky. Consider the human urge to hold magnets to sand, to make iron filings trace lines on paper, to see with our eyes what our skin cannot feel. To imagine the future, let your mind span centuries. The field will continue to wander. North will continue its journey across ice and ocean. There may be a reversal, not tomorrow or next year, but someday. We will watch it begin, the field weakening slightly, the dipole tilt changing, patches of reversed polarity blooming like islands before the full swap. We will see auroras at lower latitudes more often. The South Atlantic anomaly may shift and change. Satellites will adapt. Power grids will prepare. Life on the ground will notice mostly in the skies. Through it all, the field will remain, thinner for a time, and restored. The shield story is not of perfect constancy, but of resilient persistence. Push farther into deep time. The inner core will grow, grain by grain, as iron crystallizes in the center of the earth. That growth, paradoxically, feeds the dynamo as long as the heat flows sustain convection. Far in the future, hundreds of millions to billions of years, the core may cool enough that convection weakens, and the dynamo might dim. If we're still here, we'll have become a spacefaring species, carrying our own magnetic shields when we travel. A laughably modest replica, perhaps a local field draped around a spacecraft. We already do this in small ways, dreaming up plasma shields and using magnetic fields in laboratories and hospitals. An MRI suite hums with strong, human-made magnets, turning spin into images, an intimate echo of the planet's own practice of using magnetism to reveal hidden structure. And then there are worlds beyond. When we think about habitable planets, we'll fold magnetism into our criteria with quiet care. Not every living world will need a strong field. Some could be protected by thick atmospheres, or live under oceans or ice. But a magnetic shield is one graceful way the universe seems to make life easier. The search will look for radio whispers from auroras, for subtle dips in starlight that hint at magnetic interactions, for atmospheres that endure in the face of bright, active stars. We will translate Earth's lessons into hypotheses, and the sky will answer with surprises, as it always does. What does it mean, emotionally, to be held by an invisible shield? Perhaps it means we are part of a larger kindness, the kindness of physics that allows complexity to breathe. Our planet has a heart that moves. That motion becomes a field. That field shapes space. And inside that shaped space, oceans do not boil, air is not torn away, and sunlight becomes food. It's a cascade of fortunate processes, but not miraculous. Understandable, measurable, repeatable. And in that understanding, there is a special kind of awe. The more we see, the more grateful we become. On a quiet night, step outside. Let the air touch your face. If you live far north or south, and the sun has been restless, you might see auroras, ribbons of light that float and fold and whisper. If you live closer to the equator, look up anyway. The field is there, though you cannot see it, arching over you, diving into the ground beneath your feet. Somewhere deep below, a river of molten iron moves in slow spirals. Somewhere above, satellites listen to the field snap and sigh as the solar wind plays its long cello note. You stand between skin warmed by the air, mind warmed by the thought that you are sheltered by the planet's own handiwork. There is a quiet invitation in all of this. An invitation to rest, knowing that the world is careful in ways you cannot sense. An invitation to learn, to let gentle curiosity guide you deeper into cores and skies, into histories of sailors and scientists, into the songs of birds and the flicker of polar light. And an invitation to belong, to feel that you are part of a planet that has been looking after life for billions of years with an invisible, steady arm. Thank you for listening, for breathing with this story, for letting the science become a lullaby. If you'd like to drift into more calm curiosity with us, more quiet shields and slow wonders, you're warmly welcome to subscribe and rest with the next story when it arrives. Until then, may the sky above you be kind, and may the earth's quiet shield hold you gently as you sleep.